you can see I was after molarity as solution concentration. That's moles of solute per liter of solution. Stoichiometric coefficient is that number to the left of the reactant or products that give relative amounts, relative number of moles. C, I was after products, is the substances that are shown on the right side of the reaction arrow. Aqueous is the term we use to describe something that's dissolved in water. Yield, I believe is it EI or IE? I can't remember. But yield or percent yield is the ratio of what you actually got to what you thought you should get. Gross error is an error that is associated with somebody's ineptness. And solution is another name for a homogeneous mixture that we talked about in Unit 4. So down here at the bottom, I ask you a few questions about that balanced chemical equation. What are the products? Of course, the products are on that side, so it's the ACl3 and the H2O. What are the reactants? That's the aluminum hydroxide and the HCl hydrochloric acid. That's B. Question C, what physical phase is the aluminum hydroxide in? Since it's got an S next to it, it's solid. D, what's the coefficient in front of the aluminum chloride? And since there's nothing there, actually, we know it's 1. Let's see, I wonder if... Okay, then we go on to balancing equations. And I'm not going to go through each one of these. Really, pretty good. Of course, the one that kind of threw people off was the D. Okay, so you can kind of take a look. This, let's see, it's not posted yet, but it will be posted yet this afternoon, this answer key under doc sharing. So D kind of threw people off. It's possible that your set of coefficients looks different than my set of coefficients, and that's because they're scaled differently. Okay, and if I counted it wrong, but you say, no, it's really the same, I scaled it up, okay, or scaled it down, come and let me know. But those are the balancing equations. Then on to the next page. Okay, so actually there were a couple of stoichiometric calculations. No, this isn't a stoichiometric calculation. This is a solution concentration problem. So in this one, they ask for how many grams of KMnO4, potassium permanganate, are in this volume and this molarity of solution. So you are going to need the molar mass. In some cases, this is worth 6 points. In some cases, if you didn't get the molar mass right, I could see that that's the issue and I could take off fewer points. But to do it all in one step, what I would do is first off make sure, and I didn't see that I did it, but if you unpack molarity, this is molarity. Okay, unpack molarity. What that 0.252 m means is 0.252 moles of KMnO4 per 1 liter of solution. Then if we start with our volume and go ahead and get our volume into liters, okay, then we can go ahead and use the molarity to get liters to cancel, and we're left with moles. And then, of course, you probably recognize that last term is the molar mass. So rounded to 3 sig figs, I got 11.0 grams of KMnO4. Another solution problem, question number 5, it gave you the mass of NaCl, and it gave you the total solution volume, and it wanted the molarity. So again, we're going to have to go from grams to moles at some point. So this first calculation, I knocked out the molar mass of NaCl. Then what I like to do with this sort of problem is basically put the mass over the volume that was given. And if I stop there, I have units of grams per milliliter, but I want moles per liter. So what I did here was to fix the bottom to get it in terms of liters, and then this third term here is my molar mass. That is the molar mass. And if we use that, then actually grams will cancel. We'd be left with units of moles. So notice that grams here have canceled with grams here. Okay, milliliters cancel. Okay, and we're left with actually units of moles per liter, which is what we wanted. 3 significant figures, it's 0.318. So question number 6. was a stoichiometric calculation. We're given that balanced chemical equation. Notice I put under the aluminum what we knew. We know there's 5.552 grams of aluminum. We need to get to grams of oxygen. Okay, so we'll need the molar mass of molar mass of aluminum, and actually the molar mass of oxygen. One of the things you need, if you see a stoichiometric calculation on your final exam, which you might, okay, just know that when you calculate these molar masses, okay, these molar masses didn't have anything to do with those stoichiometric coefficients. We're still struggling with that a little bit, okay? They have nothing to do with the molar mass. So they do have something to do with that stoichiometric ratio we're going to use, okay? So, all right, so then start with the mass of aluminum, and then use, in my answer key, start with the mass of aluminum. The second term really should be the molar mass of aluminum. Okay, notice we do this to get grams of aluminum to cancel. We left with moles of aluminum. And you recognize this is the stoichiometric ratio. Always include units for full credit. On your comprehensive final, those last questions, the ones where you do not fill in the bubbles. Multiple choices fill in the bubbles. But those last problems, what did I say? They're worth 8 points apiece? 6 points apiece. So in order to get full credit, you're going to have to show all of your work. So the multiple choice ones, you can just doodle away. Okay. So anyway, if we go from grams of aluminum to moles of aluminum using its molar mass, use a stoichiometric ratio to get from moles of aluminum to moles of O2. Then once we have moles of O2, we can use the molar mass of O2, which is 2 times 16, or 32.00 grams per mole, to get to grams of O2. So rounding it to through 4 significant figures, because that's what we're allowed in the original mass of aluminum, you get 4.938 grams of O2. On to the next page. Last page? Next page. So yeah, there were 2 stoichiometric calculations on this, because number 7 is also a stoichiometric calculation. Basically, you're given the grams of C2H2, and you need to find the grams of CO2, in A anyway. So we'll need the molar mass of both of those things. So you can see I kind of knocked it out up front. So it's kind of like the pattern we looked at in the previous problem. In this case, we have grams of C2H2. We can get to moles of C2H2 using the flipped version of the molar mass, which is the second term. Whoops. There it goes. Okay, there's the molar mass. The third term we can get from moles of C2H2 to moles of CO2 using a stoichiometric ratio. And then the last term we can get from moles of CO2 to grams of CO2 using CO2's molar mass. So it's a very similar pattern. So yeah, there'll be something like this on your final, along with all sorts of other different things. For B, it kind of piggybacks on A, and some of you maybe recognize it, some of you didn't. But basically it's saying, what if we had that same mass of C2H4, okay? The beauty of that same mass means that actually this up here, this was then a theoretical yield. Theo yield that you calculated there. So if that's our theoretical yield, now we can go ahead, and B goes on to say, what if instead of getting 165 grams, what if instead of getting 165 grams, you only got 144.9? So that's kind of where the problem is. So basically it's a ratio of 144.9 grams over 165 grams right here. So that's where that goes. And then the last one, actually we call this kind of like a titration problem, but a solution stoichiometry problem. If you read it a few times, you can kind of see what you know more about and what you're trying to get. Notice I usually kind of pull out from the problem what we know most about is the HCl. We have volume and molarity of HCl. What we have about the Na2, sodium carbonate, is the volume, and we're trying to get to molarity. So the three problems look like this, like we've kind of the pattern we've been talking about in lecture. Okay, so if we start with the moles of HCl, or go for the moles of HCl, and notice if I label here, I don't have to be explicit in my problem. We had 50 mils of HCl at 0.367 molar. So we take the volume, we convert it to liters, and then we use the molarity to get to moles of HCl. The second part, we've been talking here, once you have moles of HCl, go ahead and get to moles of sodium carbonate using the stoichiometry. 2 moles of HCl for every 1 mole of sodium carbonate. So the moles of HCl will cancel, and we have moles of sodium carbonate. And then to knock it out, in this case, since we're after molarity, we can take those moles that we came up with and divide it by the volume that was given. And since molarity is in terms of moles per liter, we have to do one more correction to get the milliliters to cancel. So the molarity of that solution, given that information, is 0.330 molar. So